Welcome to the Deep Dive. We plunge into fascinating topics so you can emerge, well, truly well-informed. Today, I want you to try and imagine the farthest, darkest parts of our own cosmic backyard. The outer solar system. It's this place that, even with all our powerful telescopes, it's still pretty much shrouded in mystery, full of potential hidden wonders.
It really is a genuine frontier right here, practically on our doorstep.
Yeah.
And every single new discovery out there, it really has the potential to just rewrite how we think our solar system even formed.
And that's exactly what we're trying to do in this deep dive. We're going to unpack a brand new discovery, a very rare object called a Sednoid, nicknamed Ammonite. And it's already, it's making astronomers rethink quite a lot about our solar system's very distant past. This deep dive is based on some really cutting-edge science. We're talking recent observations of the Subaru telescope in Hawaii, some crucial follow-ups, and fascinating insights from simulations discussed in Nature Astronomy.
Yeah, a good mix of observation and theory.
Exactly. So our mission today, to figure out what this discovery actually means, why it's so significant for understanding how the solar system formed, and maybe what other exciting revelations might be just around the corner. So let's start with just how challenging it is to explore the outer solar system. I mean, when we talk about these really distant regions, we're dealing with places that get incredibly little sunlight.
Barely any.
Which makes detecting anything, especially these trans-Neptunian objects, TNOs, unbelievably difficult.
Yeah, it's often called a game of patience and precision, and for good reason.
Right. So what kind of, painstaking work actually goes into spotting objects this faint? And how did Ammonite first pop up?
You're absolutely right. It takes immense effort and incredibly sensitive instruments. But that precision really paid off here. It led to this new discovery. 2023 KQ-14, quickly nicknamed Ammonite.
Ammonite, okay.
And what makes this so remarkable, so instantly noteworthy, is that it's only the fourth Sednoid ever found.
Only the fourth.
Yeah, that tells you straight away just how rare these things are, these unique objects. The first detections of Ammonite, they were made back in March, May, and August of 2023. They used Japan's Subaru telescope in Hawaii, specifically its amazing Hyper-Suprime Cam.
Right.
It was part of this really cool program called the Formation of the Outer Solar System, an Icy Legacy Survey, or FOSSIL for short.
Fossil, I like that.
Yeah.
Okay, so detecting it is one thing, but you need to really pin down its orbit accurately, right?
Yeah.
That sounds tricky. What happened next?
Exactly. Those initial detections are really just the first step, kind of like seeing a flicker in the dark. The really crucial follow-up observations came in July 2024 using the Canada-France-Hawaii telescope.
Okay.
And then the team combined that with digging back through archival data, looking for previous potential sightings, and that whole process. It extended Ammonite's observational arc to an incredible 19 years.
19 years for something just discovered. That sounds vital. Why is having such a long observational arc so important for these distant objects?
Oh, it's absolutely critical. It's the key to accurately pinning down the object's precise orbit. You see, when you're dealing with things that are moving so slowly and they're so incredibly far away, you need observations that span many, many years to truly understand their path around the sun. A few snapshots just won't cut it. As Dr. Fumi Yoshida, one of the astronomers involved, put it quite well, understanding the orbital evolution and physical properties of these unique, distant objects is crucial for comprehending the full history of the solar system.
Makes sense.
It's like piecing together a cosmic puzzle from, billions of years ago. You need as many pieces over as much time as possible.
Right. So, okay, we've established Ammonite is rare, hard to spot, but you have this 19-year arc now. Its classification as a Sednoid, though, that seems to be the real key to its significance. Can you walk us through what exactly defines a Sednoid? Why are these objects such critical pieces in this solar system history puzzle?
Absolutely. So Sednoids stand out because of their truly extreme orbits, really unusual paths around the sun. First, they have very high eccentricity. That just means their orbits are extremely stretched out, very elliptical, not neat circles like, say, Earth's orbit.
Okay, so long and skinny orbits.
Pretty much, yeah. And second, they have incredibly distant perihelia. That's the closest point to the sun. For Sednoids, this closest point is always beyond 60 astronomical units, or AU.
60 AU. And Neptune's at about 30 AU, right? So twice as far as Neptune at their closest.
Exactly. They never get anywhere near the main planets. And finally, their semi-major axes, which is basically the average size of their orbit, are huge, beyond 200 AU.
Wow.
So these are just, random chunks of ice out there. They're very specific extreme orbits hint that something profound shaped their paths. orbits.
And this is where Ammonite immediately caused a stir, right? Because it's perihelion, that closest point, it actually fell into this specific puzzling gap that the other sednoids hadn't filled. Tell us about this Q gap.
Precisely. So before Ammonite, astronomers noticed this perplexing gap, a sort of no man's land for sednoid perihelia. It was roughly between 60 and 75 AU. Theory suggested sednoids should exist there, but, well, none had actually been found in that range. The three previous ones we knew about Sedna, 2012 VP113 and 2015 TG387, they all had perihelia outside that 60-75 AU zone. Then along comes Ammonite with a perihelion measured at 66 AU. Bang, right in the middle of that previously empty gap.
So it fills the gap. Its orbit is unique compared to the others in that sense. But then you mentioned numerical simulations, and there's a fascinating twist there, isn't there?
Yeah.
Despite these orbits looking different now, what did the simulations suggest about their ancient history? Way back when?
Yes, this is where it gets really intriguing. You run these complex computer models backwards in time, essentially, and despite their current orbits being quite different perihelia, different overall shapes, the simulations show that all four sednoids, including our newcomer Ammonite, they likely shared a very similar orbital configuration, clustered together in a way about 4.2 billion years ago.
4.2 billion. That's incredibly early in the solar system's life.
Extremely early. It strongly hints at a shared ancient origin story for these objects. It suggests that whatever force, whatever event sculpted these extreme orbits, it probably acted on all of them in a similar way, way back then.
And that, of course, leads us straight into one of the biggest ongoing cosmic detective stories out there, the Planet 9 hypothesis. For what, over a decade now, this strange clustering of orbits, especially among sednoids and similar objects, has fueled the search for a hypothetical massive planet, Planet 9.
The idea being that its gravity is sort of shepherding these distant TNOs, keeping their orbits aligned in a peculiar way.
Right. So here comes Ammonite. Does this discovery strengthen the case for Planet 9, finally give us a smoking gun? Or does it complicate things?
Well, this is where it gets really interesting. Ammonite's orbit being somewhat misaligned compared to the others, especially the ones that originally sparked the Planet 9 idea, it actually complicates the picture quite a bit. It significantly lowers the odds that a single, distant Planet 9, all by itself, could be responsible for sculpting all these extreme orbits.
So it doesn't quite fit the neat pattern predicted by the simplest Planet 9 models.
Exactly. Its unique trajectory kind of doesn't align perfectly with what you'd expect if only one massive perturber was out there pulling the strings. It forces scientists to think more broadly.
Okay, so if a single Planet 9 isn't looking like the sole answer anymore, thanks partly to Ammonite, what are the alternatives? What else could have created these bizarre sednoid orbits? We're talking some pretty wild ideas, aren't we?
We really are. Ammonite's orbit forces us to open our minds to a much more dynamic, maybe even more chaotic early solar system than we previously pictured.
Like what?
Well, one possibility, mentioned by Dr. Yukin Huang, who worked on the dynamics in the paper, is intriguing. He said, it is possible that a planet once existed in the solar system, but was later ejected.
Ejected? A whole lost planet.
Imagine that. A sibling planet that got kicked out early on, but maybe its gravitational influence lingered or helped shape these orbits before it left.
Wow. Okay, what else?
Beyond a lost planet, you've got other possibilities. Maybe ancient stellar flybys, another star passing close enough to our sun billions of years ago to gravitationally nudge these objects.
A drive-by star affecting our outer system.
Could be. Or maybe rogue planets, planets not bound to any star drifting through the neighborhood early on. Or even interactions within the sun's birth cluster. Remember, the sun wasn't born alone. It formed in a cluster with other stars. Things could have been pretty crowded and messy back then.
Right. Lots of gravitational interactions.
And another idea is capture. Maybe sednoids didn't even form here, but were captured from other passing stars.
So, lots of potential culprits. But the core idea seems to be that something external must have done this, right? Because Neptune can't explain it.
That's the fundamental point. Sednoids' perihelia, their closest approaches are just too far out. They're well beyond Neptune's significant gravitational reach. So Neptune couldn't have lifted their orbits this high and kept them stable there. Some external actor, as you say, must be responsible. The Nature Astronomy paper is pretty clear on this. No known planet in our current solar system can account for these raised perihelia.
So Ammonite, by not fitting neatly, it really pushes us towards these, well, more complex, maybe more violent early solar system scenarios.
Precisely. It suggests the early solar system wasn't a calm, orderly place. It might have been full of gravitational encounters, migrating planets, maybe even lost ones.
It really does make you feel small, doesn't it? Thinking about all these cosmic interactions billions of years ago. So, with these possibilities ejected planets, rogue stars, are we basically rewriting the first chapters of our solar system story?
In a very real sense, yes. Each new discovery, like ammonite, especially one that doesn't quite fit the existing models, forces us to refine the narrative. It chips away at assumptions and paints a much more intricate, grander picture of how we got here.
And this hunt for answers, it's definitely not slowing down. In fact, it feels like we're on the verge of a huge leap forward with the Vera-Rubin Observatory.
Yeah.
You just saw first light, right? That's a big milestone.
That's right, a huge milestone. The Vera-Rubin Observatory is poised to kick off its decade-long survey, the Legacy Survey of Space and Time, or LSST. This observatory it's specifically designed to catch faint transient objects, things that change or move against the background stars.
Perfect for finding TNOs then.
Absolutely perfect. It promises to completely revolutionize Kuiper belt exploration and our whole understanding of the outer solar system. Its ability to scan the sky deeply and repeatedly is just, well, unprecedented.
So looking ahead, with LSST coming online soon, what are the big questions you think it might finally answer? Could it actually find Planet 9, corner it once and for all?
That's certainly one of the hopes. LSST has the potential, if Planet 9 exists as hypothesized, to spot it, or at least spot many more objects whose orbits point towards it. Or it might uncover dozens, maybe hundreds, more sednoids like ammonite. It could fill in that Q gap completely or reveal entirely new patterns in these distant orbits. Finding more of them will give us much better statistics to test all these different origin theories, Planet 9, stellar flybys, lost planets, you name it.
So either way, we're going to learn a ton.
Oh, definitely. It's going to be an absolutely incredible decade for planetary science. The data floodgates are about to open.
What a journey we've been on just discussing this one object. So let's recap this deep dive a bit. We've explored the discovery of ammonite, this incredibly rare sednoid. We talked about its puzzling orbit that actually falls into that previously unexplained Q gap. And crucially, how this single object significantly challenges the simpler versions of the Planet 9 hypothesis.
Yeah, it forces us to consider a wider range of possibilities.
Exactly. It's opened up this whole spectrum of diverse, maybe even wild possibilities for how the early solar system evolved. It really highlights this amazing blend of cutting-edge observations, long-term computer simulations, and these big new surveys coming online.
It's just a powerful reminder, really, that even in what we think of as our own cosmic backyard, there are still these profound mysteries waiting to be uncovered. And sometimes, just one single faint object spotted billions of miles away can completely unravel years of established thinking.
Indeed. And maybe it leaves us with this thought to ponder. If these incredibly distant objects, like ammonite, are telling us our solar system was once far more dynamic, maybe more chaotic than we ever really imagined, what other profound secrets are still waiting out there, literally at the edge of our vision, ready to reshape our entire understanding of home?